Hello, I'm Brian Cruz, CEO of New Sapiens, one of the few companies in the AI field today that's working not on narrow AI, but on artificial general intelligence. Another company who's been chartered to do AGI is OpenAI. OpenAI is the creator of ChatGPT, the large language model that has created so much excitement and controversy in the last few months. Recently, OpenAI has gotten, of course, lots and lots of attention, and its CEO, Sam Altman, was recently interviewed. And during the interview, he was asked, what kind of competition do you fear for OpenAI? And he went on to say he was dismissive that the large tech companies like Google or Microsoft would be a threat, since they were doing the same thing. In fact, Microsoft is a huge investor to the tune of $10 billion in OpenAI. No, he said the thing he would fear the most would be basically what he called two guys in the garage who have a totally new approach to AGI. He was asked if he had his eye on such a company. He said, yes, he did, but wouldn't reveal who. Now, that could describe us pretty well. We have no way of knowing if he does have his eye on us. But the idea of two guys in the garage solving a problem when all the combined might of well-financed companies like OpenAI, as well as the big tech companies themselves, are not solving is pretty revolutionary, or at least it seems it is. By the way, nobody really argues that ChatGPT is AGI. Everyone would agree that it's narrow. It doesn't have general intelligence. But think back a ways. It was once a time, not long ago, that the idea of the two people in the garage with the new technology that grows up to disrupt the world was a cherished ideal of Silicon Valley. And all the big tech companies we have today really started off most that way. So that is our story too. Just a few people with a truly unique idea that will grow up to change the world. This session 5, Synthetic Intelligence 101 series, is that story, our story, the origins of the Sapiens and synthetic intelligence. Our objectives is first to understand the synergies that come from a truly interdisciplinary approach. Without being interdisciplinary, with having only one set of principles, you only have kind of one way to solve a problem. And as they say, if the only tool you have is a hammer, every problem looks like a nail. And then to appreciate the power when you blend the theoretical with the practical perspectives. And finally, understand why it was that New Sapiens, and not big tech, government, or academia, that made the breakthroughs that led to Sapiens. When I was 16, I decided I needed a philosophy of life, or at least my perspective to look out on the universe. And I don't remember why, but I know I had two guiding principles. One is described perfectly by this quote from John Muir. When you try to pick out anything by itself, you find it connected to everything else in the universe. And the other one was the scientific method. Now, I went on from there from high school, that was back in high school, to St. John's College in Annapolis, Maryland, where we studied the great books of the Western world. And it was a great place to see what people had to say about epistemology, about how we know what we know, moving forward, and how the worldview of the times from the ancient to the medieval to the modern day, where how the view of the world changed. And I was really struck by something, and that was that what we know of the world, that is the most powerful knowledge we have of the world, isn't a bunch of facts or statements of truth or fundamental principles, so much that it is a model of ideas that are self-supporting and connect together into sort of a mechanism, even a clockwork mechanism. And the ancient Greeks had a model which had the Earth at the center. This is the model of their whole cosmology of the universe. And based on that, they put together an intricate mechanism. It was a thoroughly scientific theory, but it utilized different premises than the ones we came to rely on later. It had the Earth at the center going on regular circular motion. And this elegant mechanism, in fact, they even built clock works. In the lower corner here, you see the Antikythera mechanism. It's been modernly reconstructed to track all the motions of all the objects in the heavens. And it was practical. You were able to navigate a ship around the surface of the planet with a simple device like a sextant. Later, of course, we came by and we said, oh, it's a better model, a different model is to put the Earth at the center and use different premises, not regular circular motion, but force at a distance and gravity and momentum. And we created a Newtonian universe. And you could still use it to navigate a ship around the world, but with some caveats. When I left St. John's, I didn't go and become an epistemologist. I regarded St. John's as a wonderful theoretical background, but you might say I was ready for my practical education. And to achieve that, I joined the US Navy and became a naval aviator. And within a few years, I found myself navigating our aircraft around the surface of the world. Special mission C-130s like this one in the picture here. And we had to use our navigation, a thoroughly Newtonian device, which was based on force at a distance acceleration. It had inertial navigation platforms and accelerometers and performed some very sophisticated calculus on board to derive displacement, starting with a given point to a current point based on accelerations. But it was very complicated, way more complicated to just navigate around the surface of the Earth than you would have the Greek systems. But when it failed, as it sometimes did, what did we do? We got out a sextant, took a star shot, looked at the tables, and the tables we used were essentially the ones that Ptolemy had laid down in Alexandria 2,000 years earlier. So it really came to me, it really brought home to me that models are what we know about the world, and that they're carefully put together and integrated. And knowledge is just not a bunch of facts. So this became, to me, kind of the foundations of a new epistemology. From aviation, I wanted to get into space business. We got a master's in space systems engineering, went back to Sapiens, and soon found myself working on the Hubble Space Telescope program in Greenbelt, Maryland. And there, I took on myself, I found a kind of a personal mission to change the way satellites were operated. In a nutshell, I wanted to be able to operate the Hubble Space Telescope in a way which is more like the way we operated C-130 aircraft, with beautiful displays which told you right now what you needed to operate the vehicle. What I found when I got to NASA was that they were operating the spacecraft like science projects, and everyone had to look at numbers presented on screens, and all the big computers in the ground system did was converted the raw measurements into engineering units. And I said, this is kind of crazy. We need to get those computers to take those numbers and convert them into information about the state of the vehicle and its subsystems, so we can operate it with assurance, the way we operate airplanes. And that led me into AI, artificial intelligence. And at that time, artificial intelligence meant expert systems, which were not based on my epistemology, based on kind of the older epistemology that saw truth as a bunch of facts. And expert systems, essentially one fact at a time, put in the coded into symbols and put in a rule and processed in a big computer. You could go through long chains of reasoning to come up with the right answer about some fairly difficult analysis. But it took lots and lots of rules, and it took lots of computing, and they were slow. But NASA liked my idea. I built a prototype of using an expert system, and NASA funded me to go to the Lockheed AI Center in Palo Alto, where they were training engineers in AI techniques. And while there, I met some of the scientists there, and I said, what we need to do is create an expert system that has so fast performance that we can keep up with the telemetry stream, because we need that for Hubble and for all spacecraft operations. And that kind of caught fire, and we built the first real-time expert system. And we did build at least prototypes for Hubble, but we soon found out that the bureaucratic inertia of big tech companies aerospace companies at the time, and NASA really made it difficult to really get move very fast. So we founded, I involved with them to found a company called Tellurian to commercialize this real-time expert system shell, which we licensed from Lockheed, which was an interesting journey. Got some venture funded, and went on and started getting our first contracts to apply the technology. But expert systems didn't really scale. Too many rules, too much effort, too much development, and it really never got traction. What it did, the company though, Tellurian actually had to pivot. They kind of ultimately gave up expert systems, and they took the inter-process communication they built to distribute the processing over multiple computers as middleware, and eventually were acquired by another middleware company, which went public in 2000. And there was a lesson to be learned there. But the most important lesson for me, if I wanted to do spacecraft operations in an automated way, was expert systems weren't going to do it. But that expert systems, symbolic AI, it was the first big wave of AI. And in its day, it generated lots of hype. So phase two, though, not giving up. Phase two of how do you put knowledge into the machine? And I ended up starting another company, Altair Aerospace, specifically focused, not particularly on AI, but solving the automation problem. So we quickly abandoned knowledge representation and symbolic AI, and we came up with an entirely new approach. And that was, we built a tool that allowed a space systems engineer to invited them to think of their spacecraft and map the knowledge of that spacecraft into a state machine, a finite state model, which consists of a top-level system. For instance, top-level system might be the Conestoga launch vehicle, and it would have subsystems like propulsion, electric, hydraulic, all the different subsystems that a launch vehicle might have, or a spacecraft might have. And then what are the different states that those subsystems can be in? And then how do we map the states of the lower level components and the subsystems into the top level state? So it turns out that was a natural, because spacecraft engineers already kind of thought about their vehicle as a state engine. And what we did is we harnessed the new object-oriented software technology and the new concept of markup languages. So we invented a markup language which allowed the engineer to specify their state model with a very simple syntax. It did not require programming or of any sort, just a little skill in how the syntax and the symbols go together to represent the symbol and represent the spacecraft. And then we wrote a kind of compiler to create and compile that information directly into an object structure in the computer memory. So for the first time ever, we had what was arguably a human knowledge curated from human minds in a computer. And we applied that to first the Conestoga launch vehicle, and into a number of other satellites, as well as in the military side. I had stayed in the Naval Reserve and was assigned to the Naval Space Command and worked with Navy space officials, including Bill Reedy, the NASA astronaut, who he was the XO, I was the CO, I was the XO for a while, Naval Space Command. And we took the same technology that Altair made available and applied it to some military space systems. But the Conestoga launch control system was probably our crowning achievement at the time. It was the most highly automated and most successful launch control system of its day. It costs a fraction, maybe 10% of what a traditional control system would have cost. And when other control systems were running on mainframes, we were running it on PCs. And it proved itself beautifully. So it looked like my dream of revolutionizing spacecraft operations was on the verge of being realized. When, fate having it, all the investment in commercial space went away due to some spectacular commercial failures from Globalstar and Iridium. Motorola lost $5 billion. They missed the market to cell phones. So the commercial contracts that we were pulling in kind of dried up, and Altair was sold to a public company, Aeroflex, in 2000. But over these first two phases, first and second, a lot was learned. And the first one was, knowledge isn't really a representation. It's a model, and models don't represent things. They kind of resemble things. For instance, a picture is a model. And that's why we say a picture is worth 1,000 words. Words are symbols. Models are much more compact. The next thing was keep the data and the code separate. The beautiful thing was all of our information, all of our knowledge, keeping the data and the code separate is just, that's a fundamental principle of good programming practice. But we did more than that. We took data and we mapped it into information, and we took the information and created that very special type of information structure, which is knowledge, which is the models of the world. So it was kind of the ultimate separation from the code and the data, in that very complex knowledge of how spacecraft operate. Literally rocket science was encoded in this model structure, which was initially static at runtime, and the code that processed it was incredibly simple. It would just, you start a little program that invokes a method at the top level object structure and invokes a method that says find your state, which queried the lower level states. It was about as complicated software-wise as a washing machine controller. And yet we created higher levels of automation of the most complex systems in the world out there than had ever been achieved before. And still, believe it or not, we learned that the more sophisticated the data structure, the simpler the code. We learned that this idea of providing intermediary tools and languages that can provide a powerful bridge between concepts in the mind and computational information. But you have to go through a translation and a transformation process of several phases to go from one to the other. But that process is unique. It's neither communication in the sense of using language to talk or tell something about something like humans do between each other, nor is it programming. It's neither programming nor communication. It's modeling. The other thing is aim to solve real problems, because even if you miss your mark, you may solve another problem. And that was the case with Tellurian. They had to build inter-process communication because expert systems required so much processing power that we had to put our product on 3 separate mainframe computers. And at the time, there wasn't the inter-process communication utilities and languages that we have today. So we had to write those from scratch. And that ended up being the Tellurian's ultimate product when expert systems didn't pan out. In fact, today, a lot of the financial information that travels around the internet travels on the original bus or its successors that Tellurian and built. But I wasn't part of that. I bailed out because I was focused on space. And so finally, a great technology doesn't imply a viable market. And that's a whole nother story. In the end, after the commercial space dried up, we naturally had interest from government customers. But and even though they seemed like they wanted to buy it, it turned out that there were always barricades why they couldn't entrust these very difficult systems basically to a small company, but B, even more important, that it's an automation technology. So think of that huge ground system that the space station has with tens or hundreds of highly trained people in it. You know, that's kind of their crown jewel. You bring in our kind of automation technology and you can do the whole thing with 3 people. That was a non-starter with NASA. I know that because we tried. We were even invited to unsolicited proposal for the space station ground system from the director of manned spaceflight at the time, who was had a personal relationship from the Space Command. We still couldn't get it done. So Altera was sold to a company in 2000, a public company, as I mentioned. So phase 3. So I had an exit. So I actually had 2 exits because my first company eventually went public. And I had some time to think about what I had learned. And after a while, I started going back to my epistemological theories of my undergraduate days and putting it together with what I'd learned about putting knowledge into machines through my career in space technology, and asked the question, could we take such a process of curating human knowledge through intermediate tools, not something specific and narrow like a spacecraft, but any general knowledge of the common sense world? Could we build a model of the common sense world and put it into a computer? And the answer was not necessarily obvious overnight that one could do that, or how you would go about doing that. But in 2004, I teamed up with Carsten Honeycutt, who's a brilliant Duke graduate in computer science, double major in Russian. So he was both a computer science and a linguist. And we started to explore the problem and how we would create such a structure that was not necessarily linguistic or made out of words, how we would build it, what would the tools look like. And we went through a few iterations so there was about a 10-year R&D until we really figured out how to do it. And then after 10 years, I was ready to start talking to outside investors. And I met Bill Bandy, the gentleman here in the upper right in corner with the big smile and the gray beard. Bill worked at DARPA, PhD physicist, had been at DARPA, had been eventually became involved in microelectronics and was a founder of a company called Matrix, which eventually was acquired by a public company for $240 million. And he has his name on probably 200 different patents. So he was one of the first people I went to who said, wow. He said, when I was at DARPA, I would go down all the time down the hall with the AI people. And I would always go down and say, hey, you guys invent a machine that understands what I'm talking about yet? Can understand me when I speak to it? No. But he said, I always thought that the way you were approaching it would be kind of the way it would succeed. And he said, go off and get a working prototype and get a patent on file and come back to me. And I did that. And he became my first outside investor. And to date, our largest investor. And he's on our board and is also our chief intellectual property officer. So we got that patent in 2016, which was a rather short time. It was rather surprising to me. There was nothing else out there. Of course, the patent office always, denies the first time, but the things they said were prior art were pretty lame. So it was not hard to get the patent. We have many more disclosures and work now that we've actually built the system. At that time, it was based on how the fundamental ideas were there, but not the actual implementation. So the cognitive core, that all important thing, that kind of like digital DNA, which underlies it, really came into fruition around 2017. About that time, or shortly after, not long after Bill Bandy came on board, another a person I guess you would call a polymath, and a person of interdisciplinary background, Tom Loveland, who's the president of a company called Mind Over Machines, who has also attended St. John's, studied mathematics at the University of Chicago and history of ideas at Washington State, a wide thing. He also immediately saw that he was something different and something that really could be revolutionary. He's now also on our board of directors and also the chief admin officer of the company. And he's, again, one of our largest, probably our second largest investor. More recently, Bill Reedy, astronaut from my Naval Space Command days, and later has also joined the company on the board of directors and as our strategic relationships officer. So we're not the typical two guys in a garage. We're not, young guys. We've all had multiple companies and exits, except for Carsten. But Carsten had plenty of time to mature in the last 15 years. So we are the two guys in the garage because we did something completely different with very little resources that no one else has been able to do. And it was because we were just a handful of people. It was because we weren't locked into the process and procedures of a large company, and because we had unique backgrounds, I should say, and from different directions to come together to figure this out. So it pretty much brings us up to date right now. We are porting our engine over to the Swift programming language, so it can run natively on the iPhone, which is pretty amazing. And we are making very rapid progress now. We are expanding our staff. We've made several new hires right now, and in just a few months from now, we are going to be demonstrating some things that people thought were beyond the reach of AI, at least for decades. So, thank you. Our next session, which will be session 6, we're going to talk about the amazing scalability of our technology. And in the end, again, that scalability, meaning so much functionality for comparatively small effort and resources, whether in programming or modeling or computational resources. It's unique to our approach, but we understand exactly why it's so scalable. So that'll be a very interesting session. I hope you join it and join us for it. In the meantime, there's lots of information online. newsapiens.com is our main website. Lots of interesting papers and articles there. My Sapiens is focused on our first consumer product, which is going to be a digital personal assistant that you'll have on your cell phone that will, we believe, change your life. Forward to the Future is my blog site. We have a YouTube channel with some videos on them if you haven't already seen some of those. That's where these sessions are ending up.